going to talk about quadric surfaces. This is a large class of surfaces that will be useful to us as we move through the semester in not only providing us a set of nice examples to apply our new Calculus 3 knowledge to, but a collection of surfaces that actually arise in application. For example, we see spheres arising in physics and chemistry, cylinders, for example, the one that we see here, a pipe, for lack of anything more exotic. So these kinds of things arise naturally in application. There's another thing down here called there's a hyperbolic surface, hyperboloid, and we see them in cooling towers in all kinds of situations. We see parabolic reflectors, these parabolic dishes. So lots of applications involving what we call quadric surfaces. I may accidentally say quadratic surfaces. They're one and the same. These are surfaces whose equations fit this very broad general definition. If you look closely at this, what we see are squared terms of so the independent variables are of course x, y, and z because we're working in x, y, z three-dimensional space. And they occur as a sum of terms, and those terms can be square terms, they can be cross terms like x, y, x, z, y, z, they can be linear terms like x, y, and z, and there can be a constant, and they're all set equal to 0. And the whole variety of quadric surfaces can be generated by just choosing these constants a, b, c, d, e, f, g, h, j, and k appropriately. And in fact, we see a summary of the different kinds of surfaces that we encounter in this very useful table. This table shows the general form of this particular important class of surfaces, ellipsoids in this case. Ellipsoids are sort of the generalization of an ellipse to 3 dimensions, and they are characterized by a quadric equation of this form. We see only the square terms, and we see them occurring only with positive sign. And then the constant term 1 out here on the right-hand side. So if we compare that to this very general equation, we can see that a is actually, in this case, 1 over little a squared, b is 1 over little b squared, c is 1 over little c squared, and k is -1, and it's been moved over to the right-hand side. And the remainder of these constants are all set to 0. In that situation, you get an ellipsoid. If we continue, you take this same equation and you change the sign on one of the terms. So this was plus here, now it's minus. You get the hyperboloid of one sheet. Continuing, if you change the sign on two of the positive terms on the left-hand side, so we start off with this ellipsoid and we change the sign on one of the terms to a minus sign, we get a hyperboloid of one sheet. If we change the sign on two of these positive terms, in this case x squared and y squared, but it could be z squared, all that's going to do is change the orientation. We get a hyperboloid of two sheets. Continuing, if we change the sign on one of them, but set the k term to 0, so very similar to the hyperboloid of one sheet, but the big difference being the k term is 0, the constant term is 0, you get what we call an elliptic cone. Continuing, if we if we look at these two, how do they compare? Instead of having z squared, so you could imagine taking this, right, and moving the z squared over to the right-hand side. And you'd have x squared, an x squared term plus a y squared term equals a z squared term. If you take that term on the right-hand side and change it to a linear term in z, then what you get is something called an elliptic paraboloid. This is kind of the analog to a parabola in 2 dimensions, but in 3 dimensions it's kind of a bowl-shaped thing with an elliptic cross-section. And then last of this zoo of quadric surfaces, we have the hyperbolic paraboloid. This is kind of interesting because you can kind of see in the xz plane it's a parabola opening upward, and in the yz plane it's a parabola opening downward, and it's kind of this cool mix of the two. And you can imagine this place right here is sort of like a saddle. And indeed, we call this point a saddle point, which we'll see later in the course. These are the most common quadric surfaces. You might say, hey, what about a sphere? Well, a sphere is actually an ellipsoid. It's just that these constants a squared, b squared, c squared are all equal. So that's the zoo of surfaces that we're talking about, and all of them flow from this single equation. And remember, from our earlier conversations, an equation is a membership test. If you're a point in XYZ space and you plug in your coordinates here and you satisfy this equation, then you're a member of the surface, you're part of the surface. So the reason these points are highlighted as opposed to these points out here away from the surface is they all satisfy this equation. Our goal here for this section is to be able to identify and sketch these various kinds of surfaces, and to understand how to look at intersections of these surfaces with planes to get a grip on their behavior. Big idea, narrative, I've already kind of gone through it a little bit, but this is sort of the next step up from lines and planes. Lines and planes are sort of linear in nature, and quadric surfaces, due to the presence of these square terms, are what we call quadratic. They have these quadratic terms in them, quadric surfaces. That's where the name comes from. And as I mentioned, they're good examples because they're simple and they come up a lot in application. Okay, I'm going to leave most of the reading to you and jump to a selection of exercises from the end. So let's get started with some of the exercises. The first one that I want to talk about is problem 304. Yeah, pull up the text here. Let's jump down to problem 304. So here we're asked to sketch and describe the cylindrical surface of the given equation. In 304, we're looking at x squared plus y squared equals 9. And you don't see a z variable here, so context is important. If I were to ask you to sketch this curve in 2 dimensions, you would sketch a circle centered at the origin of radius 3, and you'd be done. But that's not the context we're working in. So in 2D, this is a circle. In 3D, this is a cylinder. And the reason for the difference is in 3D, we're assuming that there are 3 variables in play, x, y, and z. And even though we don't see a z in this equation, it's still there. So one way to start your sketch or your understanding of this particular surface would be to sketch that circle in the x, y plane. And recognize that, of course, if you're thinking about x squared plus y squared equals 9 as a membership test, of course, all of the points on that circle in the xy plane satisfy this condition. What's true about the z-coordinate for all the points along the circle in the xy plane? The z-coordinate is 0. Well, there's nothing special about z equals 0. In fact, z can be anything. So z could be 1, for example, which would give us this circle floating up here 1 unit above the xy plane. Or z could be -1, which would give us this circle down here 1 unit below the xy plane. Nothing special about 0 or 1 or -1 either as a z value. In fact, z can be anything. And so what you get is a cylinder. Any point on the surface of this cylinder will satisfy this equation. And that's why it has the form that it does. So that was exercise 304. Let's look at our next exercise, 306. In problem 306, we're to repeat the process only with a different curve, z equals e to the x. So for z equals e to the x, again, we're assuming 3D. So in 3D, we have an x, y, and z variables that are in play. We see that y is missing, which means it can be anything. Y can be anything. So we're going to have to take that into account as we try to understand this surface. All right, let's look at just the xy plane at the moment. Sorry, the xz plane, x and z. Why am I focused on that? Because those are the variables that we have in the equation. And let's sketch that thing first. You should know, just from prior experience, that the exponential function looks like that, and it always passes through the point 0, 1. How do we introduce or sort of understand this surface in full 3 dimensions? We add a y-axis, and all we do is we extend the curve out in both directions. And we repeat the same kind of thought experiment. If y was equal to, say, -1, it would, the points along this curve would still be satisfied, right? We could still kind of sketch a section of the curve there sitting at -1. And if y were 1, there'd be a section of the curve out here. And that's just sort of how it works. And you extend in both directions, sort of parallel to the y-axis. And I'm murdering this sketch. If you really want to see what this sketch looks like, you should jump over to a visualization tool like GeoGebra and have a look. In fact, we could do that. Let's jump over to GeoGebra and see what this curve looks like in 3D. So I go to geogebra.org, I go to the 3D calculator, which lets me plot 3D curves, 3D surfaces, and give it a chance to start up here. And you know, when you're working in the 3D calculator, the implicit assumption is that we're working in 3 dimensions. So I can type an equation like exp x, and it knows that you're working in 3D, so it knows to extend it indefinitely in both the positive and negative y directions. If you look at it just edge on in the xz plane, you see the familiar exponential curve. But if you glance a little bit askew and you include that y dimension, you see that this is a surface that extends away parallel to the y-axis. This too is called a cylinder. It doesn't look like a cylinder, but any kind of surface that's constructed from a curve and then extended parallel to some axis is considered a cylinder in this mathematical context. So that's 306. I'm going to group 310 and 311 together because they're related. And let's grab a little bit of space here. So for 310 and 311, we're given a couple of surfaces. And we're asked to specify the name of the quadric surface and determine the axis of symmetry of the quadric surface. All right, let's, and probably is worth grabbing these instructions. And in fact, let's also grab the 2 plots. So 310 311. Ooh, that's quite large. Let's shrink that down a little bit. And give ourselves a little more space. And grab the next one. 311. All right, almost got our ducks in a row here. Also coming in quite large. Let's shrink it down a little bit. All right, we've got these two figures, which we really can't even get on the same page. Specify the name of the quadric surface. I think the easiest thing to do is just to kind of go and let's compare this quadric surface to the zoo of quadric surfaces that are enumerated here. And if we scroll down, it's clearly not an ellipsoid, not a hyperbola. It could be this, it could be this. And we look at these two and we see that in this one, the two lobes, the upper and lower part of the surface, are touching at a point, whereas up here, the two lobes, the upper and lower part, are not touching. So this looks a heck of a lot like the second one, something we call an elliptic cone. And the axis of symmetry appears to be the z-axis. And I'm just getting that from, oh, I'm sorry. I spoke a little bit too quickly. Here's the z-axis cutting across. Here's the y-axis also cutting across the lobes. Here's the x-axis actually appearing to go kind of straight through the middle. So I'm wrong. It's the x-axis, is the axis of symmetry. We can't rotate this thing, but it's the axis that kind of goes through, right through this point and then out the other side, and exactly centered inside this surface. Let's look at this one. Again, we see a surface now of two lobes, and there are only a few surfaces that have these lobes, these separate pieces. We talked about them, but these two lobes are separated, much like the hyperboloid of two sheets. So here we can identify a hyperboloid of two sheets. And the axis of symmetry, again, you can see the x-axis passing through the middle. That's the axis of symmetry. That's the axis that the lobes are opening up around. If you were asked to sort of identify the rough form of the equation, you could go over and look at this. And you can see that when the z part is positive, it opens along the z-axis. Here we see it's opening along the x-axis, so we could expect that the x part would be positive. So we'd see something like x squared over a squared minus z squared over c squared minus y squared over b squared equals 1. So in this zoo, it's really important to note these kind of patterns and connections. We don't always have the hyperboloid of one sheet opening along the z-axis, but when the negative term is the z-axis, that's what we see. Similarly here, these lobes don't open along the z-axis always, but when this positive term is z squared, then we see that. All right, let's continue. We want to talk about problem 334 now. So 334, jumping over to the textbook. For the following exercises, find the trace of the given quadric surface in the specified plane of coordinates and sketch it. All right, so we want to find the trace of this surface in this plane, the y equals 0 plane. Let's grab that. It's relatively straightforward. What you're doing is you're looking at the set of points that satisfy this, whose y-coordinates are 0. If the y-coordinate is 0, then we can immediately set y equal to 0 in this equation and get minus 4x squared plus z squared equals 100. And then we have to think about, well, what kind of surface is this? this is not a circle, if it were, or an ellipse, I guess that's what I'm trying to get at. This is not an ellipse. What kind of thing is this? It's not an ellipse because this is negative and this is positive. You may remember from your work in pre-calc or maybe in calculus that this is actually the equation of a hyperbola in 2 dimensions. In 2 dimensions. Which 2 dimensions are we talking about? Well, which 2 variables are present? Well, we have an x variable and a z variable. So usually when I'm trying to plot hyperbolas, I just plug in a couple of points and I know kind of generically how they should behave. So I'm going to look at x equals 0, for example. When x is equal to 0, z is plus or minus 10. And I'll just use a smaller scale here. And when, say, x is equal to 1, then I have z squared is equal to 104. So that's a little larger than 100. And so we're going to get, for say x equals 1 here, we're going to get something a little bit bigger. And when x is equal to -1, a little bit bigger, and a little bit bigger. And so you can immediately sort of see that we're tracing out 2 lobes of a hyperbola opening along the z-axis. That's what the trace of this surface in the y equals 0 plane looks like. Why would we do this? Well, we might repeat this experiment for, say, z equals 0 and x equals 0, and get a pretty good idea of how the surface is interacting, even in the absence of some kind of plotting tool like GeoGebra. So sometimes it's useful to kind of just see how a surface is behaving in a slice along a particular direction. 334, that was 334. Let's move on to 338. Oh, you know, before we move on to 338, let's go back to 334. What kind of surface is this? Let's go and compare it to the zoo. So we see 2 positive square terms and 1 negative square term and a constant on the right-hand side. If we were to divide through by 100, that would introduce a 1 here, but this would still be negative, positive, positive. So let's go look for something like that. A 1 on the right-hand side and negative, positive, positive. So let's go up to the zoo. A 1 on the right-hand side, negative, positive, positive. So this is going to be a hyperboloid of 1 sheet. And we see that whatever square term is negative, that's the axis that it will open along. If we go back here, we see that the negative term is on x, or on x squared. So we would expect this thing to open along the x-axis. And you can kind of see that here. If this is the slice in the xz plane, this is the opening. This here is the opening. And the opening is along the x-axis. So this is a hyperbolic sheet, or a hyperboloid of 1 sheet, opening along the x-axis. So that zoo, that table in the section, is pretty useful to help us further visualize the surface. 338. Let's talk about 338. So in 338, we're asked to use the graph of the given quadric surface to answer the following questions. Let me grab that. Move it over to our notes. And maybe make it a little bit smaller. Great, now we're ready. Add a little space. Might be a good idea to, well, in fact, part A is to figure out the name of the surface. So we see this surface, it has one lobe. So we're looking at surfaces that have a single lobe. Let's go up to the zoo of surfaces. It's not an ellipsoid, not a hyperboloid. This has two lobes, that has two lobes. Probably an elliptic paraboloid. Let's go back. Yeah, I'm going to call that an elliptic paraboloid. Now, if we look at how the axes are oriented here, we see the xy plane down here on the bottom and the positive z-axis above. The entire surface is above the xy plane. So that means that the points that are satisfying this all have positive z coordinates. If you look closely at, for example, this first possibility, there are three possibilities here: this equation, this equation, this equation. Which of these equations corresponds to the surface? If you look closely at this, the right-hand side of this equation is positive. 9x squared plus y squared, that's always positive. The left-hand side, we have a negative 36. So any points that satisfy this membership test must have negative z coordinates. So think that through carefully. Any points that satisfy this membership test must have negative z coordinates. And there are no points on this surface that have negative z coordinates. So we can immediately rule out that one. Let's jump to the last one because I happen to know that it also is not the correct answer. For this one, it's a little less obvious. The right-hand side has a mixture of positive and negative terms. So maybe we'll look at a trace and see if we can understand the surface a little bit better with a trace. And I'm going to look at the trace where x equals 0. So let's consider, in this case, let's look at the x equals 0 trace. What should that look like? If we set x equal to 0, what remains on the right-hand side is 4y squared, and on the left-hand side is negative 36z. Once again, we would expect only negative z values to satisfy this. So if we look at x equals 0, we have a positive right-hand side, 4y squared, and a negative left-hand side. That means that only negative z values can be on this trace. Well, if you look at this trace along the x equals 0 slice, right, what does that look like? That's a parabola in this trace. And you see that parabola is opening upward, positive z values. So this, too, doesn't describe the surface that we're dealing with. Now, by process of elimination, we're left with this third equation, and that's the one that describes the surface. You could verify a little bit here. So the left-hand side is positive, the right-hand side then as plus 36z is only going to have positive z coordinates, and so at least we're comforted with the idea that this thing is pointing in the right way. It's above the z-axis. Let's use B to write the equation of the quadric surface in standard form. So we've identified an elliptic paraboloid. We've identified its equation. How do we put it into standard form? Let's go back to the book and see what the standard form for an elliptic paraboloid is. That involves solving for z and then rearranging things so that we can figure out what little a and little b are. So the standard form is z equals, let me switch back to black. The standard form is z equals x squared over a squared plus y squared over b squared, like that. How are we going to do this? It looks like we just need to divide by 36. So in our case, z is going to be, what's 9 divided by 36? That's 1/4. So x squared over 4, aka 2 squared. And y squared, what's 4 divided by 36? That's just, 1/9. And we'll write y squared over 3 squared equals z. Oop, we already have equals z. And this is the standard form. You might be wondering, the question's not asking this, but you might be wondering, what are the 2 squared and the 3 squared giving us? The 2 squared is telling us that in this direction, we've got, or not really in this direction, but if we took a sort of a cross section of this thing, what we would see is a collection of ellipses. They're growing in size, but kind of the ratio of the axes of the ellipses would be 3 to 2. 3 in the y direction and 2 in the x direction. So it's kind of giving us a sense of the eccentricity of the cross-sectional ellipses. And we can see that because 2 is very close to 3, this ellipse is not very eccentric. It's not very stretched out. It's much closer to a circle. But that's a side question, not something that was asked for in the exercise. Moving on, let's talk about 344. In 344, use the method of completing the square to write the equation in some kind of standard form and then identify the surface. Let's make a copy of that. Drop it in here. So this is clearly some kind of quadric surface because it fits that very general equation that it was introduced in the section way up here. Way up here. Right, it looks a lot like this. The constants are different, but in general it just kind of fits this pattern. How can we identify which quadric surface this is? We can do a method called completing the square. I've done this in earlier lessons, but we'll repeat it. Let's gather the x terms together and complete the square. So if we take x squared plus 2x and complete the square, that's x plus 1 quantity squared. By rewriting x squared plus 2x in this way, we get the x squared, we get the 2x, but we add an extra term of 1, which we should remove by subtracting 1. Doing that takes care of these two terms. There is no other y squared, there is no other y term, so I'm just going to carry the y squared along right now. There's no completing the square that's necessary, and that will resolve the y squared part. The z squared part, there are a couple of z terms, so we'll write z minus 6. Minus 6 is just half of minus 12, the coefficient on z. We square that. Doing that gives us the z squared term and the minus 12z term, but it introduces a plus 36, which we have to remove. And then finally, the 37 goes along for the ride. Oops. And we're left with an equation that looks like this. Cool. Let's simplify a little bit. The minus 1 here, the minus 36, and the plus 37, they all cancel. That's a net 0. And we have x plus 1 quantity squared minus y squared plus z minus 6 quantity squared equals 0. Okay, this is introducing an idea that we don't really see in the zoo of surfaces that we've been referring to all along. Here we just see x squared plus y squared plus z squared, or x squared plus y squared minus z squared, and so on and so forth. We don't see terms that look like x plus 1 squared or z minus 6 squared. My hope is that with a little bit of explanation and your past experience, you can maybe guess the effect that x plus 1 squared is having or z minus 6 squared is having. If you think about it a little bit, what's going on here is all we're doing is shifting the whole surface in the x direction or in the z direction according to this plus 1 or minus 6. We're just moving the surface around. We're moving it, sort of shifting it in the x direction by minus 1 and in the z direction by plus 6. And we're not doing any shifting in the y direction. So hopefully that seems natural to you with your experience with spheres, for example. Okay, let's look carefully at the signs on these quadratic terms and of course the right hand side and see if we can figure out what kind of surface this is. So there's a 0 on the right-hand side. In other words, there's no constant term in this entire equation. This has a constant term floating around, so it's not an ellipsoid. This has a constant term, so not a hyperbolic sheet. Constant term, not a hyperboloid of two sheets. An elliptic cone has no constant. An elliptic paraboloid similarly has no constant. And a hyperbolic paraboloid, no constant. So it's got to be one of these three. Let's see if we can eliminate things a little bit further. Here we see that there are three squared terms. And in the elliptic paraboloid and the hyperbolic paraboloid, there are only two square terms and then a linear term in z. So it can't be either one of these. So we're left with the elliptic cone with three squared terms. Now let's focus on the signs of those terms. We have two positive quadratic terms and one negative quadratic term. That's consistent with what we see here, two positive quadratic terms and one negative quadratic term. Which one is negative? The y quadratic term is negative. Jumping back over here, we see that the negative quadratic term is the axis about which the elliptic cone opens. So that means that we have an elliptic cone that's opening along the y-axis. So we have an elliptic cone. Let's switch again back to black. So by comparing to, this must have a name, yeah, the characteristics of common quadric surfaces. And I wonder if it has a label. Yeah, figure 288. By comparing to fig 288, we see that this is an elliptic cone, and it opens along the y-axis, and it's shifted to the point -1, 0, and 6. It's shifted to the point -1, 0, and 6. We've done a lot of sort of hand waving here, and maybe not hand waving, but introduce some ideas that are not explicitly in figure 288. This idea of shifting, completing the square, and introducing these shifts is something that I expect you to kind of understand and incorporate into your general knowledge of quadric surfaces. Continuing, let's talk about 356. In 356, we have a hyperboloid of one sheet and an elliptic cone. And they're both sketched, and they intersect each other. And the question is to find the intersection of the curves and maybe find their equations. All right, let's talk through this. This is something that we have to be really careful about in Calc 3. It's not like Calc 1 and Calc 2 when you're finding the intersections of curves and you just set them equal to each other and you solve and everything is wonderful. In Calc 3, it's a little more involved. It involves a little bit more mathematical reasoning than what we encounter when we're just working with two-dimensional curves. So I want to carefully walk through this exercise so that you can understand the differences and sort of the new sophistication that we're going to encounter in Calc 3. So remember that equations are membership tests. I'm on the hyperboloid of one sheet if my coordinates satisfy this equation. I'm on the elliptic cone of that's described right here if I'm on this surface. And I've got to kind of figure out which kinds of points satisfy both. just before we continue, I want to make sure that you're clear that this piece right here is the elliptic cone, and this piece right here that looks like, say, a nuclear cooling tower in a nuclear plant, that's the hyperboloid. This might not look like an elliptic cone. If you go back and look at what elliptic cones look like on the zoo, there's the elliptic cone. This doesn't look maybe a whole lot like an elliptic cone. Gosh, let me get back to it. If we could rotate it around a little bit, we would see that these two sides kind of come in and touch each other right here in the middle. And then if we could extend this out a little bit, we would see much more of sort of this elliptic, this lobe kind of going off in this direction and this lobe going off in this direction. So just take my word for it that this is a correct representation. And we're interested in where these intersect. All right, let's start talking through this. Let's talk about the set of points that satisfy both of these equations. We want to get that in our head. So consider, in fact, I'm going to type a little bit because I'm a little bit faster of a typer than I am of a writer. So we want to consider the set of points that satisfy both equations. All right, let's pretend that we're thinking about the set of points that satisfy both equations. And if you stare at these two equations, imagine adding them together. If we added them together, we would get rid of this x squared term. So let's try adding them together. And this is a very ad hoc process, and you kind of get an intuition for it as you work more problems. Let's try adding the equations. We know that we're thinking about the set of points that satisfy both equations, so both equations are true under our assumption. So it's safe to add them together and see what kinds of additional information comes from adding them together. When we add the equations together, why did we do that? Because the x terms are going to cancel. And that might simplify our lives and help us kind of extract information. And that's what we're talking about here. We're talking about doing algebra and kind of extracting information about the set of points that satisfy both equations. If we do that, what we're left with, in fact, I guess I'll write out the whole thing. 25x squared plus 25y squared minus z squared equals 25. That's the first equation. And the second equation is negative 25x squared plus 75y squared plus z squared equals 0. Adding them together, we get 100y squared. And it looks like the z squareds also cancel, so that's kind of nice, equals 25. So we know that if for the points that satisfy both of these equations, this is also true, that y squared is equal to 1/4. How did I get that? I just divided both sides by 100. And from which it follows that y is either plus 1/2 or minus 1/2. So we've learned something about the set of points that satisfy both of these equations. Every single point that satisfies both sets of equations has its y-coordinate as either 1/2 or minus 1/2. That's pretty interesting. So we have two cases to think about if we want to kind of get more information. Case 1. Let's assume not only that we've satisfied both equations, which is how we got here, but let's also assume that y is equal to 1/2. And we'll think about the negative 1/2 case separately. So if y is equal to 1/2, let's go back up to equation 1. Let's substitute into equation 1. Y equals 1/2. That yields 25x squared plus 25 over 4, right? Because y is 1/2, y squared is 1/4, minus z squared equals 25. This is interesting because it tells me that the set of points that satisfy both of these equations has this trace. This is the trace of the intersection, or indeed this is the intersection curve and it sits in the y equals 1/2 plane. So the intersection curve is in the y equals 1/2 plane, and it looks like this. Looks like there's, let me think about this a little bit. Let's divide by 25 just to clean this up a little bit. X squared minus z squared over 25 plus 1/4 equals 1, like that. And let's move the 1/4 over to the right-hand side. Just kind of winging the algebra here. This is kind of how things work. Move the 1/4 over to the right-hand side. So that leaves me with a 3/4 on the right. A lot of times it's useful to maybe get the right-hand side into a standard form. That would mean turning it into a 1. So maybe we'll divide by 3/4. X squared over 3/4 minus z squared over 25 times 3/4, like that, equals 1. Okay, what kind of figure is this? This is a hyperbola. And it sits in the y equals 1/2 plane. So the curve of intersection, at least part of the intersection, is a hyperbola of this equation, and it's opening kind of along the z-axis, and it's sitting here at y equals 1/2. So we can mark y equals 1/2 right here. I'll mark it in red. And maybe you believe that that's sitting right there. That's sitting right there on the y equals 1/2 plane. You can probably guess what's going to happen over here on the back side. This is the negative 1/2 plane, y equals negative 1/2. And there's going to be a trace of it back in here. And this is the hyperbola, right? This is the hyperbola on the front. In fact, let me sort of label these in different colors. All right, so the green one is going to correspond to y equals negative 1/2, and the red one is going to correspond to y equals 1/2. All right, so let's think about this. Have we answered the question? Identify the intersection curves and find their equations. So we did find one intersection curve and its equation. That's this one. And you might be able to guess that when y is equal to negative 1/2, you plug that in here, and you're going to end up with the same intersection curve. The only difference being that you're on the y equals negative 1/2 plane instead of the y equals 1/2 plane. So here it's the same equation in x and z. So it's a hyperbola, and it's on the y equals negative 1/2 plane. What you notice here is there's not much sort of setting equations equal to each other and solving. It's much more of a reasoned approach, or a mathematical / logical approach. try this yourself, play around with it a little bit, and see if you can work a problem on your own. Okay, the last problem for the lesson, 360. All right, we have these magnets, so-called rattlesnake eggs, and if you're not sure what a rattlesnake egg is, here's a video. They're just these very hard sort of ceramic magnets, and when they bang together, as we'll see in this video, they kind of make an interesting noise, and they're ellipsoids.
Zvukova ima. Znači kao neke zvečarke. Evo još jednom. Da. Drugo, prilično su jake.
So because they're magnets, they're attracted to each other. That's essentially what you're being asked to sort of model that surface. Oops, I thought I'd grabbed that. Let me go back. And so the idea here is to write an equation that describes the surfaces that model these sort of oval-shaped rattlesnake eggs. We first identify them as being ellipsoids. So if we go back to the textbook and look at our, what's the word I'm looking for, our zoo of surfaces, we can see, let me get this section open again. Give the browser a chance to render things. If you can't tell by the clock, I went away and ate lunch, did a couple of other things, and now I'm back. Okay, so we are looking at an ellipsoid. This is the shape that most closely resembles these rattlesnake eggs. The equation for the ellipsoid is x squared plus y squared plus z squared, x squared over a squared, y squared over b squared, etc. So we're trying to figure out essentially what are a, b, and c. So we have x squared over a squared, y squared over b squared, z squared over c squared equals 1. And we know that these oval-shaped objects, each one is 1.625 inches long. 1.625 inches long. And we know that each one is 0.5 inches wide. And if you were to take a cross-section here of the ellipsoid, it would be circular. That's the assumption that we're going to make. So how do we kind of get this oriented so that we can describe it in a graph? Indeed, let's just drop a set of axes right here. Let's put the origin here. Let's drop a set of axes in here and here and here, just like that. So this is x, y, and z. Now what we can see is we can identify actual points that are on this surface. For example, this point right here, let me change colors. This point right here that I've marked in red, what's the x-coordinate for that point? It's essentially half of 1.625, and that's the x-coordinate, the y-coordinate is 0, the z-coordinate is 0. Just for the sake of presentation, I'm going to call this this value right here, I'm going to call this value L for the length, and I'm going to call this value width for the width and the height. We know that they're equal. So using these variables, so I don't have to keep writing decimals all the time, we see that the x-coordinate of this point is going to be L over 2, and then the y-coordinate is 0, and the z-coordinate is 0. And this is on the surface. What that means is it satisfies the equation of the surface. And we can use that information to figure out a squared, b squared, and c squared. Let's see how that works. So I know that this point satisfies this equation. So I'm going to substitute in x, y, and z into the equation. And what I get is L squared over, well, let me be a little more careful. What I get is L over 2 quantity squared divided by a squared. Now, y is 0, so that term goes away. Z is 0, that term goes away. And so this is equal to 1. And remember what we're trying to find. We're trying to find a. So multiply both sides by a, and what we get is L over 2 quantity squared equals a squared. And now we very quickly identified that a is equal to L over 2. How do you think we can repeat this to figure out b and c? Well, we can repeat this by identifying a second point on the curve. Let's go along the z-axis, and let's pull out those coordinates. If I'm sitting on the z-axis, I'm looking at a 0x coordinate, a 0y coordinate, and some non-zero z coordinate. Well, how high is this above the xy plane? Well, it's going to be half of the width of this ellipsoid, so 0.25. And just so I don't have to carry around a bunch of decimals, I'm going to use w over 2. So here's another point that I know is on this surface, so it must satisfy the equation. So let's repeat this exercise: 0 for x, 0 for y, w over 2 for z. And I see that w over 2 quantity squared over c squared equals 1, and this immediately leads to c is equal to w over 2. All right, what about the remainder? We have two different ways of figuring out what b is. We could go for a third point on, let's take this one right here. This is back along the positive y-axis. And we can repeat. We know that this point has x coordinate 0, y coordinate is going to be w over 2, z coordinate is going to be 0. I can substitute that into the equation, and I'm going to learn that b is equal to w over 2, which this is the same as c in this case. In this choice of coordinate systems, if you look closely at this cross-section right here that I've just shaded in gray, that's actually a circle. It's a circle of diameter 0.5 or a circle of radius w over 2. And what we would expect in that slice we have x equals 0. So this term is gone. And what's left behind is x squared over b squared plus z squared over c squared equals 1. If we want that to be a circle, b had better equal c. And in fact, that's what we're seeing here and here. B and c are equal. So that's an equation that represents this shape. It's somewhat dependent on my choice of axes, but in the usual way that I've been drawing axes in this class, that's the equation. You might choose to have the long end going along the z-axis and the short end going along the x and y. You're going to get a similar equation, but not exactly the same. The second part of this is actually a mystery, right? The equations of the prolate spheroids that model the shape of the buzzing stunt magnets, I'm not actually sure what they mean by that, so I'm just going to kind of kill that. But I am interested in the second part, to use a computer algebra system, CAS, to create the graphs. GeoGebra is a computer algebra system, and so let's jump over and plot our final answer. And I guess I should give you a final answer. That would be best practice. X squared over a squared, which is L over 2, quantity squared, plus y squared over b squared, w over 2, quantity squared, plus z squared over c squared, which is also w over 2, quantity squared, equals 1. And let's punch that into GeoGebra and see if we can't observe something that looks very much like one of these rattlesnake eggs. So I'll pull up the 3D calculator, I'll clear out our previous work, and let's punch in the equation for this spheroid. So I know that L is equal to 1.625. I know that W is equal to 0.5, and the equation is of the form x squared divided by the quantity L over 2, quantity squared, plus y squared divided by the quantity W over 2 squared plus z squared divided by the quantity W over 2 squared equals 1. And there you have it. We can zoom in and we get something that looks quite a lot like one of these rattlesnake eggs. Okay, so work through these exercises. The suggested exercises are essentially all of them at the end of the section. Do enough of them so that you're comfortable with the concepts and material, and then jump over to web work, and you want to take the assessment C2S6 quadric surfaces. Thanks a lot.